Hello and welcome back to Essentials of Computer Architecture and Organization. We're continuing on in our second major section that we want to cover in Coomer's textbook, and we're talking about caches and caching. To start out with, this is a fairly straightforward concept, but as we move through the latter parts of this chapter, it'll get a little bit more difficult. And so I would like to just walk you through this information and give you a survey of how this works. And if some of it gets a little bit complicated to follow, you're welcome to pause and both use a textbook and use this information to review perhaps a couple of times. So don't feel overwhelmed, but let's go ahead and get started. So in general, caching is a key concept in computing. It's used in hardware and software. A memory cache is essentially used to reduce von Neumann bottlenecking. And if you remember, we talked about having bubbles flowing in a computing pipeline, and this is a way that you could start to figure out how to minimize this. And this block diagram, I think, will help to begin to give the overall concept. So it acts as an intermediary. It is located between the source of requests and the source of replies. So requester could be the central processing unit, and then it's having to engage with the large data storage. If you have a buffer, this may be another way useful to conceive this, that you start to get information here and put it in a more accessible way. So it's a lot faster to communicate with a cache the way it's designed versus the larger data storage, which is slower and has a lot more memory that it can store. So it contains a temporally local storage that's very high speed and limited size. A copy of selected items is kept in the local storage in the cache. Cache answers requests from the local copy when possible. So you're using this higher speed set of memory contents, and instead of having to go all the way to the large data storage, you just communicate back and forth with the cache. So what are some of the characteristics of the cache? It's usually small, much smaller than the storage needed for the entire set of items. So it starts to have more of a characteristic of memory versus a hard drive of some sort, maybe even getting towards the performance of what you would be thinking in terms of a register. It's active. It makes decisions about which items to save. Some of that can be based on different algorithms about what makes sense for it to hold on to, and kind of have a, quote, training sequence, if you will. And we'll be talking a little bit more as we move to the latter part of this chapter. It's transparent. It's invisible to both the requester and the data storage. And so this gets into an interesting example of, quote, virtual memory, that the asking device doesn't really need to know the information of where it's coming from. But if this ends up making the performance a lot faster, it's definitely an advantage. And lastly, it's automatic. It uses the sequence of request. It does not receive extra instructions. So it's not anything new. It's just taking the existing information and processing it in a faster way. So there are a range of possibilities that can exist for this. It can be implemented in hardware, can be implemented in software, or it can be a combination. Small or large items can be considered. It can be a byte of memory or a complete file. It can be textual or binary data, and it can be something that would be dedicated for an individual processor or shared among processors or among cores if you have a multi-core processor. It can be retrieval only or store and receive, so there's different possible modes. And it's one of the most important optimization techniques available, and we'll have an example of that later giving you an idea of how much speed improvement can come up from this. So let's talk about some cache terminology. You can have something called a cache hit, and that would be the first thing. The request can be satisfied from the cache. So the cache miss means that the request cannot be satisfied from the cache. So the cache does not store it, so you have to go all the way out to the regular memory. Locality of reference refers to whether the requests are repeated. High locality means many repetitions, and low locality means few repetitions. And one other thing to consider is cache works well with high locality of reference. So now let's talk about, in terms of cache performance, talks about how we would quantify the cost performance. And so we have this little bit shown differently, this diagram we had before. We have the requester, we have the cache, and then we have the large data stores. So the CH is the cost of an item found in the cache hit. So it has a lower cost when it just has to go to the cache and return. The CM is the cost of an item not found in the cache and it missed. So it goes to the cache, nope, it's not there. So I have to go all the way out to the large data store to get it. So that's just a little bit of insight. So let's analyze the cache performance. The worst case would be for a sequence of n requests where none of them can actually use the advantage of the cache because it has to go all the way to the regular memory. So, and the other case, the best case is for an n set of sequences. All of them are able to go to the cache to restore except for one. So that's going to have a lot better performance. And so for the best case, the average cost per request is, and this is breaking that down into more detail and doing a little bit of math to get the best case cost. And an interesting point here is as n goes to infinity, this term and this term go to 0, and the only thing you're left with is the cost for the cache, which is an encouraging sign. So we solve for C best. We get this. This is the final form, and as n approaches infinity, we're left with the CH cost. So what is the reason that cache works well? If we ignore overhead, in the worst case, the performance of cache is no worse than if the cache were not present. So it can only get better. So that's an encouraging point of view. In the best case, the cost per request is approximately equal to the cost of accessing the cache. And that is very promising. If we design the cache that it's very fast, we can make a huge impact in performance. So we want to note for memory caches, parallel hardware means almost no overhead. So let's have a few more definitions. Let's talk about hit ratio and miss ratios. A hit ratio is a percentage of requests satisfied from cache. It's given a value between 0 and 1, and miss ratio is a percentage of requests not satisfied from cache, and it's equal to 1 minus the hit ratio. So the hit ratio plus the miss ratio would equal 1. So this allows us to assess expected cost. Well, let's talk about the expected performance of a cache. The access cost depends on the hit ratio. And so here we have the cost. You have the hit ratio times R, 1 minus R times the miss ratio, stick that together, and that's the total cost. And R is the hit ratio. Note the cost of a miss is often much larger than the cost of a hit. The performance improvement, if hit ratio increases or cost of access from the cache decreases. So let's spend a little time and talk about the cache replacement policy. We want to recall that a cache is smaller than the data store, so it only can hold a small portion of that. Once a cache is full, existing items must be ejected before another item can be inserted. So it's the last best estimate of the things that should be in the cache, and that there needs to be an approach for doing that. The replacement policy chooses which items to eject. The most popular replacement policy is known as the least recently used, and tends to logically make sense. If it's not used recently, you're not going to have it on your shelf, if you will. You're going to stick it back into a less accessible way. This approach is easy to implement. It tends to retain items that will be requested again, and it works well in practice. So another thing that we can talk about is having multiple layers of cache. And so a multi-level cache. You can use multiple cache to improve performance. It can be arranged in a hierarchical by speed and also by cost. And so you can have like this new cache is faster and more capable in terms of speed than the original cache. And so you can see how that would be something you would want to put first. So we insert an extra faster cache and augment what was in the other previous diagram. So how do we start to analyze a two-level cache? And so here is the equation for cost. It has some similarity to what we saw before. And so R1 is a fraction of hits for the new cache, R2 is a fraction for the original one, RH1 is a cost of access for the new cache, and RH2 is a cost for accessing the original cache. Preloading caches, this is an interesting thing to be thinking about. It's an optimization technique. It stores items in cache before the request arrive. I mentioned the term prefetch before for some of the things that the Windows operating system does. And so this is what an example of this happening based on some previous understanding algorithms. It knows what to actually cache before it actually occurs. It works well if data access is in related groups. Having aspects of an application or something like that would be an example of that. When a web page is fetched, the web cache can preload images that appear on the page. And so you're going to a website and it's starting to load as much content as possible to make the experience of that web page better. When byte of memory is fetched, memory can preload succeeding bytes because it would presume that as you're looking at that, you're going to be looking at the larger aggregate of stuff that's relevant. Well, let's talk about memory caches. Several memory mechanisms can operate as a cache. Examples are the physical memory. You can have caches in there. And then there's two other things that we will cover later. You can be having a technique for caching in the virtual memory system. And the pages can operate in a demand paging system, which is also going to be covered in later chapters. So we won't spend time talking about that here other than just to mention it initially. In terms of physical memory caches, it's located between the processor and physical memory. It's smaller than the physical memory. It uses parallel hardware to achieve high performance. And we'll have a block diagram or two to give you an illustration of what that could look like. The performance, it performs two operations in parallel. It searches the local cache and sends a request to underlying physical memory. So does it contain the information in the local cache? It quickly sends it back. If it does not, or for other reasons that it knows it needs to update what it's going to be caching, it engages with the physical memory. If the answer is found in cache, it cancels the request to go to memory. There's two basic types of memory caches. They differ in how the cache will handle a write operation. So first there's the write through. Doesn't tend to be as fast. It places a copy of the item in cache, and it also sends a write to copy to physical memory. So it does two things. Write back is much faster. It places a copy of the item in cache, and it only writes a copy to the physical memory when necessary. So this works well for frequent updates, say for a loop that's increments a value. Now let's talk about cache coherence. If we have the physical memory, we have a couple processors that we're working with, and each has their own cache, but we have a singular thing that the overall processing capability is trying to do. We need to make sure that there's coherence. Each processor or core has its own cache here, and each cache can return a copy of the item. So the cache coherence is needed to ensure that correctness when one core changes an item and the other one holds a copy. So we could have some imbalances or things that may cause some issues. We can also have multi-level memory caches. Traditionally, memory caches has been separated from both the memory and the processor. To access traditional memory cache, a processor uses pins that connect the processor chip to the rest of the computer. Using pins to access external hardware takes much longer than accessing functional units that are internal to the processor chip. With advances in technology, it is possible to increase the number of transistors per chip, which means a processor chip can contain a cache. So you can actually have a cache within a CPU. Here's an example of a multi-level memory cache architecture. And it also, we have a historical note we'll get to. And the first one would be an L1 cache. This is something that would be associated with each core. So this definitely would be within the CPU. You could have a level 2 cache that it may or may not be associated with a core. So it would be something a little bit more removed. And then a level 3 cache is something that's shared among all cores. And so historical note, L1 is typically seen to be on chip. L2 would be off chip. So say it's not in the CPU, but it still may be closely associated just outside of that with a fast connection on the motherboard. And L3 would be a part of the physical memory, the RAM. So those would be possible ways of how you can have a caching architecture, multi-level caching architecture. Here's some examples of the sizes of caches that could exist. L1, that's per core on the processor. You're talking about something in the order of kilobytes, I'm sorry. L2 would be a little bit larger outside the CPU, but still relatively modest. And L3 would be shared among all cores and would be a dedicated portion within your physical RAM that would be used by this type of a caching technique. So let's mention instruction and data caching. Does it make sense to have them all together or not? Instruction references are typically sequential. They're high locality of references. So, you go from one to another. So it's definitely amenable to prefetching. I mentioned earlier an example of an application. And so there would be a lot of things that would be sequential in that type of regard. Data references typically access more randomness. There's lower locality of reference, and prefetching does not work as well in that case. So a question we can ask here is, does performance improve with separate caches for data and instructions? Well, let's explore that a little bit. Instructions and data cache, we'll continue here. Cache tends to work well with sequential references. Adding many random references tend to slow cache performance. Therefore, separate instructions and data caches can improve performance. However, if a cache is large enough, separation doesn't help. So it can improve, but especially with memory becoming more and more affordable, microelectronics becoming more and more affordable, maybe we can just defeat that by just having a large enough cache. So the current thinking is that instead of separate caches, simply use a single larger cache. There's two memory cache technologies. One is a direct mapped memory cache, and the other is a set associative memory cache. And so we'll just take a little time to talk about these two techniques, but just remember this is tend to be more of a survey, and so just take this in and follow along. So for the direct memory map cache approach, it divides memory into a block of size B. Blocks are numbered modulo C, where C is slots in cache. And so let's take an example where the block size of B is 8 bytes and the cache size is 4. And so here we have the layout here of what that would look out. And so you have the blocks here, and here is the address of bytes in memory. This is also called a direct mapping cache. Well, how does a direct mapped memory cache operation work? When bytes is referenced, it always places the entire block into the cache. The block number is n, it places the block in cache slot n. When a tag to specify, we use a tag to specify which actual address are currently in slot n. So that the tag is the relative number of the block in memory. So here's an illustration of tags. And so we can have in the cache, here it would be an example of what we would pull out. And here we're showing examples of 4 different possible tags that we could be putting into cache. And so that gives you a construct to be thinking about. Well, let's talk about efficient memory cache. We can think in terms of binary. If all values are powers of 2, bits of an address can be used to specify a tag, block, and offset. So for the example above, which is showing a really small cache and unrealistically small, but at least illustrates the points, the block size B is 8. So we use 3 bits of an offset. So that was what would be here. The cache size is C equals 4. So we use 2 bits of the block number. So that's there. And the tag is the remainder of an address of 32, which is 5 bits. And so that's what we would have in that kind of an arrangement. So here we have an algorithm for direct map cache lookup. And so what are we given? We're given a memory address. The thing that we're trying to find is the data bytes at that address. And the method is to extract the tag number T, block number B, and offset O from the address. We determine the tag in slot B of the cache. If the tag matches T, extract that value from slot B of the cache. If the tag in slot B of the cache does not match, we use the memory address to extract a block from the memory, place a copy in slot B of the cache, replace the tag with T, and use O to select the appropriate byte from the value. So kind of a high-level pseudocode just to explain how that would work. Here's an illustration of the parallel hardware in a cache. And so we have the incoming address. And here we have an example where we're selecting a particular value with its tag and the value, and then what is outputted is the value output, and whether it's valid or not. Does the information, is it found in the cache, and what is the valid output, the value output for that. So let's also talk about set associative memory cache. And so it's an alternative to direct memory cache. It uses parallel hardware. It maintains two independent caches. And so here we're showing an example of what those two caches could look like. It allows two items with the same block to be cached simultaneously. So what are the advantages of a set associative cache? It assumes two memory addresses, A1 and A2. Both have block number 0, and they have different tags. In direct map cache, A1 and A2 contend for a single slot. Only one can be cached at a given time. In a set associative cache, A1 and A2 can be placed in separate caches. Both can be cached at a given time. So the caches, these can be, you don't have to wait for one for another. You can be doing things in parallel, and the intent is to try and use that parallelism to increase performance. Let's talk about fully associative cache. It's a generalization of set associative cache. It has many parallel caches. Each cache has exactly one slot, and the slot can hold an arbitrary item. What about the consensual continuum of caches? No parallelism corresponds to direct map caches. Some parallelism corresponds to a set associative cache. More parallelism corresponds to a fully associative cache, and arbitrarily parallelism corresponds to content addressable memory. And we briefly talked about this before. And so this kind of gives you a continuum. No parallelism, some parallelism, more parallelism, and an arbitrarily large amount of parallelism. So what are the consequences for programmers? In many programs, caching works well without extra work. To optimize cache performance, group related data items into the same cache line. For example, we put related bytes into a word. We perform all the operations on one data item before moving to another data item. So how important is memory cache? Here's an example that will show you the benefit. So one day, as an operating system project, someone rewrote the processor startup code, and they inadvertently turned off the L1 cache. The performance of the system and application process was slowed. And the thing that you might want to consider is, guess how much faster the system ran with the L1 cache enabled. And I was a little bit surprised the first time I saw this answer. With the L1 cache disabled, the performance was 15 times faster. So it does make a huge difference, over an order of magnitude increase by having the cache. And so as a result of that, it makes a huge difference, and it's definitely something that we want to have, even though there's more complexity. As we've been doing all along, as we go over this course material, each lecture, each portion of this material that's Coomer has put together, we're trying to show how we can just gradually add one thing to another. So in terms of a summary, caching is a fundamental optimization technique. Cache intercepts request, automatically stores a value, and answers requests quickly whenever possible. So if we can do it from a localized store, it's going to make a big difference. Caching can be used with both physical and virtual memory addresses. Memory caches use a hierarchical approach, and we talked about L1, that would be on the processor. L2 would be between processor and the memory, and L3 would be built into the memory. And then continuing with the summary, there's two basic technologies used for memory cache, direct mapped and set associative. And we try to quickly give an example of both, and hopefully that was straightforward enough that you could follow along. Finally, fully associative cache generalizes set associative approach. Anyway, hopefully you got a lot out of this lecture. That was just a quick introduction to caching. And with that, I'll stop this recording. Thanks.